All right, these are notes on accuracy. We're going to talk about accuracy of measurements. Stop and think for a moment. You've used different measuring cups. If you are at home cooking and you are making cookies and it calls for a 1/4 cup of oil, and all you have is a measuring cup that measures 1 cup, it doesn't have any other markings on it, that's not going to be the best, most precise way to figure out 1/4 of a cup. That's why we have measuring cups in different sizes. Same with measuring spoons. Graduations are the measurements on the sides of different pieces of equipment that we use. You've used graduations of graduated cylinders to measure volume in here. Our graduated cylinders are all measured to 1 milliliter. And we've talked about you have to estimate 1 digit past that, so we estimate to 1/10. All right? So let's go ahead and get some notes down, and then we can take a look at some of this. The accuracy of your measurement is determined by the instrument. I don't know how I got a red pen, but I did. I don't know how to change the pen, but oh well. Usually, the smaller the measurement range, the more accurate an instrument is. Examples of increasing accuracy in a measurement. A meter stick that is marked in 1 meter is, you can estimate to 1 meter because you can clearly see the meter markings, and then you can estimate up to 1/10 between those 1 meter markings. A meter stick that is marked at 1.0 means it's got the decimeters marked, so then you can estimate 1 additional, which would be centimeters. A meter marked by centimeters, 100 centimeters, 1 meter, you can estimate to 1 millimeter. And a meter stick that's marked to millimeters, like ours are, you can estimate to a 1/10 of a millimeter, which is 1.0000 tenths, hundredths, thousandths, 10,000th of a meter. All right? The last digit in any measurement is always estimated. You've seen on the balance when we've tried to find the mass of substances that the last digit jumps around a little bit. That's because the balance is estimating that last digit for you. In using a ruler or graduated cylinders, though, you are responsible for estimating the last digit. Whatever you measure, you must estimate 1 additional digit further than the measuring device is marked in. As the 4 that are listed here in my, let's see if I can move my picture. The 4 pieces of equipment listed, the most accurate on here is going to be probably the 10 milliliter graduated cylinder, because it's probably graduated to 1/10, and you can probably read to 1/100th. The next one would be the 100 milliliter graduate. The beaker is the least. Oops. All right, I don't know how I did that. Go back. The least, the 1 liter graduate would be the second to the least, so we'll call it third. All right. All measured places and the 1 plus estimated place are called significant digits. Or significant figures. I tend to use them interchangeably. I tend to go towards figures. Clement and Rice tend to use digits. They're interchangeable. They mean the same thing. And I hope I'm not too confusing because I'm going to call things sig figs, and I may mean it's the same thing as significant digits, sig digs. All right, let's talk about the rules for significant digits. First of all, number one. See, I said digits instead of figures. Number one, all non-zero numbers are significant. Number two, all sandwich zeros are significant. Number three, leading zeros, in other words, dot dot or 00092, excuse me, these guys are not significant, and we'll talk about an easy way to remember it here in just a second. Trailing zeros are significant when you're talking about decimal places. So 300, those zeros are not significant, but 300, like that, those zeros are. And I know it's confusing. Easiest way to remember this is the Atlantic Pacific rule. All right, I'm going to draw a really bad United States here. And this ocean is the Atlantic. And this ocean is the Pacific. Okay? Now, if you have a number and a decimal is present, you begin counting from the left-hand side. Okay, so if you have a decimal present, such as 300.00, we start counting from the left, and we start counting at the first non-zero. That's significant. 2, 3, 4, 5. All right, if I have a number like this, I'm going to start from the left, but that's not a non-zero, so that doesn't count, and that doesn't count. Ding, ding, ding. Okay, this is because if we write 300 over 10,000, we need the zeros behind it to tell us, but we don't need any zeros in front of it. And I think I wrote that wrong. I think I need another zero. 300 over 10,000. All right. Now, if the decimal is absent, I don't know why that keeps happening. So we have no decimal. We begin counting from the Atlantic side. So if we have a number like 300, no decimal, we don't count 1, 2. We don't count those. We don't start counting until we get to the 3. So that guy would have one significant digit. This guy, we don't count till we get to a non-zero. 1, 2, 3. So let's try this. How many significant digits are in each of the following? First of all, these are all whole numbers, so there are 3. Number 2, this 0 is just it's in front of the decimal place, so that doesn't count, and we have 3 again. Number 3, this 0 is a sandwich 0, so we have 4. These are sandwich zeros, so we have 4. Number 5, now we have a decimal present, so we start counting from the left. This 0 doesn't count, this one doesn't count, this one doesn't count. 7 and 1 both count, so we have 2 significant digits. Think about if you write 70 over 10,000. You don't need the first zeros when you convert it into a fraction, so that's why we can drop those and they're not significant. Number 16, though, if we're talking about 43.00, we're talking about 43 and 00, 100. You might think, oh, that's not significant. But remember when we talked just now about measurement and estimating. If you've estimated to 2 decimal places, that means you have pretty significant data. So we have 4 in this guy. Number 7, we have a decimal present. Ding, 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 ding. We have 4. Number 8, we have no decimal presence, so we start counting from the right, and we don't count till we get to the 3. We only have 1. Number 9, we start from the left. Ding, 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 ding. 4. And number 10, we start from the right. Ding, ding, 2. Sometimes we use zeros as placeholders. These zeros are either at the end, this should be the word at, the end of numbers greater than 1, or, and again, this should be at, the beginning of decimal numbers. So those zeros are zeros like these in 71 and these in the 300, or I guess that's the only one. Placeholders are never significant. They don't represent measured places. How do you know if a 0 is significant? If it's not a placeholder is the obvious answer, but I would refer back to our Atlantic Pacific rule. At the Atlantic, if there's no decimal, we count from the right to the left. In the Pacific, if there is a decimal, we count from the left to the right. All right, with math, oftentimes we have to use the measurements we make in calculations. But the results of a value made from measurements can't be any more accurate than the measurements were in the first place. I'm going to change that word I just said. Calculation made from measurements can't be any more accurate than the measurements in the first place. This causes us to have to round results of some calculations. That should have an N in it. Round off each of these measurements to 3 significant digits. All right, decimal present, 1, 2, 3. We're going to round at that point. What's the rules on rounding? That number behind 0 is a 7. It's greater than 5. So this guy will round to 87.1 meters. The next guy, 3 significant digits. Again, we have a decimal present. We'll round here. That 3 is smaller than 5, so 4.36 times 10 to the 4th meters. The next one will begin, we have a decimal, we'll start counting. That guy doesn't count. Ding, ding, ding. So we have 0.0155 meters. Those zeros do count if we're counting, but we only want 3. We're going to stop here. So we're going to take that last 0 and round it to a 1. And I just did that wrong. We're going to round it to a 1, but we can't drop it. We can drop these 2 because they're less than 1, but we cannot drop that guy because otherwise then he becomes 901 instead of 9009. So we have to round up to 10. We round this up to 10, so we get 9010. The last one we're going to round here. He's going to become 630. Now this presents a problem because now we have a trailing 0 and we have no decimal. How do I mark that it is in fact significant? 3 ways. First, you can write it 630 and put your decimal in. Second, you can put a hat on it. And last, and the most preferred method, we could write it in scientific notation. We would move our decimal 2 to the left, so it would be 10 to the 2nd meters. Scientific notation, whatever you see is the number of significant digits. So, question, how do you know where to round to? It depends on how accurate your measurements are. Let's say we're calculating the area of this rectangle. This measurement was made to 1/100th. This measurement was only made to 1/10th. So our answer is going to be accurate to 2 significant digits because this is the least accurate. We'll take 3.24 times 5.7, and I'll do it on my calculator. 3.24 times 5.7, 18.468. Now I have to have an answer to 2 significant digits. So I'm going to round there at the decimal. So the answer would be 18 meters squared. So how do you decide where you round? If you are multiplying or dividing, you round your answer so it contains the same number of significant digits or significant figures as your least accurate measurement. If you're adding or subtracting, you round your answer so that it has the same number of decimal places as your least accurate measurement. If your calculation contains both multiplication and division and addition, subtraction, you do the multiplication and division first, then round, and then you add or subtract. Alright, so let's take a look at that. If I tell you that I have something that I have measured with one ruler and I measured 1.01 meters, and another ruler, so that was this side, and this side was measured to 1.004975. When we do the math, 1.01 times 1.004975, this guy's kind of ridiculous. All right, if I really had a ruler that accurate, that's great. But if this side is only accurate to 1/10, this side has 3 significant digits, this side has 1, 2, 3, 4, 5, 6, 7. Our answer can only be in 3 significant digits. Multiplication is pretty easy. And when you do problems in class, usually you just look at whatever digit you start with in your multiplication or in the problem, and that will tell you how many significant digits you need. For addition and subtraction, it's a little bit different. If I want to add these two together, this guy is pretty crazy specific, but adding him to this, if he's only accurate to 1/100th, we have to cut our numbers off here. So we go ahead and add it like normal. 5 plus 0, 0, 0 plus 1, 0, and we're going to cut at that least accurate decimal place. So these guys all fall off. And we don't have to round that one because the 4 was not bigger, is lower than a 5. All right. So for this guy, we're going to add 12.52 plus 349.0 plus 8.246. If I add that up, 4, 5, 6, 7, 17, 18, 19, 6, 369.766. What's my least accurate measurement? That would be the one that has 1 decimal places. So this answer would read 369.8 meters. The second one is subtraction. 74.626 minus 28.3. Again, we go ahead and do the math as usual. 46.326, but I'm going to drop it and round right there. So my answer would be 43.6 meters. I cleared that off so I could see what I was doing. The next one, 2.4526 divided by 8.4. Our answer is going to be to 2 significant digits. We don't have to worry about how many we have past the decimal place. We're just going to go to 2 significant digits. So if I do this math, and I'm not going to try to do it longhand because I'll probably screw up and then you'll all laugh at me. So I did it on the computer, and I came out with 0.29197. I need 2 significant digits, so my answer is going to be 0.29, and meters divided by meters will cancel out, so you actually don't have units for that guy. Number 4, we'll multiply the top, we'll multiply the bottom, and then we'll take the top divided by the bottom. Number 5, you have to add the ones in parentheses first because of order of operations, and then you'll divide it by that. I'm not going to take the time to do that. You guys can work that out on your own. This has already gone on long enough. Thank you very much.